to get started now. What do you reckon? Eloise, Matt?
Yeah, I'm ready to go, Matt.
Okay, so welcome to the afternoon session of the first Global Change European meeting. I'm just going to go through some etiquette slides for the meeting. For those of you attended this morning, it's a bit of a reminder. So if you're not presenting, switch off your video, mute your sound. If your sound or mic isn't working, there's a variety of different things you can test. Go to the Zoom settings, check your headset, and the last thing you could do is restart your computer. We're not really in a position to help on an individual basis at this moment. If the speaker's internet is unreliable, we'll come back to you, because that hasn't happened so far. There has been sort of it's been broken up a little bit, but not very much. So on the whole, it's worked really well so far. And if Zoom goes down, we'll have to figure something out. If you go to the next slide, Eloise. During the presentation, okay, so there's two different routes for asking a question. So if you're a presenter today, so there's a few of you here, you will have to go through the chat function. So if you go through the chat function, I will pick up those questions and I will ask those questions for you. If you're an attendee, of which there are 32 of you at the moment, 33, you can use, if you roll your mouse over the Zoom window, you'll see there is a question and answer button, and you can submit your question via that. And again, I will look at that and I'll try to, there should be enough time for all the speakers to get a few questions at the end. But I will chair all the questions that are submitted. Just very briefly, I will give all speakers 30-second warnings, just a reminder. So Danielle and Randall, you have 24.5 minutes. I'll give you a 30-second head start to the end, and you will have 5 minutes of questions. And for the other speakers, I will give you a 30-second heads up. So there's 7 minutes, 30 seconds, and you've got a couple of minutes of questions towards the end. What anything else I should ask? Okay. At the end of the session, you'll be reminded there's a networking session. So you'll be able to go in there if you have a burning question that you only thought of as we went to the next speaker, you will have an opportunity to ask them again at this networking session, and someone will circulate the links again. And there's also a poster session. This has worked really well. So you would have been distributed a whole bunch of Zoom links for individual posters. Go in there, make sure you go see them and talk to the speakers. They've put a lot of work into putting together these posters. So talk to them, ask them questions about the work they've done. Okay, good. That's a reminder of all the etiquette. So let's move on to the keynote speaker. So which is today is going to be coordinated between Danielle Jacob from Harvard and Randall Martin from Washington State in St. Louis, and they're going to give us an overview of the GEOS-Chem model. So crack on. Over to you, Danielle.
Thank you, Paul, very much. Eloise, did you give me remote control? Yep, I think I have it now. Okay, hey, good afternoon, everybody. Thank you so much for this opportunity to give you a GEOS-Chem model overview. I'm gonna share my time with my co-model scientist, Randall Martin, and we're gonna do kind of a tag team here. The piece of eye candy that you're seeing here is actually from Matt Evans' group, and it shows surface NOx in a GEOS-Chem simulation at 12.5 kilometer resolution within the GEOS Earth system model, and there will be more on that later. First thing that I would like to do is talk about what GEOS-Chem aims to be. And GEOS-Chem tries to be a grassroots, open access, state of science, atmospheric chemistry model that is easy to use and modify by the atmospheric chemistry research community. So the idea is that the community has a lot of expertise in atmospheric chemistry, wants to evaluate models with observations, try to interpret observations based on advanced knowledge, but not necessarily a lot of software engineering expertise. And GEOS-Chem is intended to deliver the capability for atmospheric chemists to do their science. At the same time, we realize that atmospheric chemistry is not in a bubble. It's a key component of Earth system science, and therefore it's very important that GEOS-Chem also be able to serve as an atmospheric chemistry module for weather and climate models. So this has been a pretty successful formula, and we now have a very large GEOS-Chem community across many countries, including many countries in Europe. Every 2 years, we have an international GEOS-Chem meeting in which we set the course for the model for the next 2 years. And then we also try to have regional meetings. We had the first GEOS-Chem Asia meeting 2 years ago, and it was canceled this year because of coronavirus. I want to give my kudos to Eloise, to Matt, and to Paul for making GCE1 happen in this virtual format. Thank you very much for making this happen. Now, what I the point I want to make is that GEOS-Chem is much more than a model. It is a community of scientists working in a cooperative way. And this is key to the grassroots success of the model, is that all the scientific development of GEOS-Chem is done by its users pursuing their scientific interests. And they contribute those developments to the standard model in a streamlined way that tries to avoid any kind of anarchy and maintain a unified front to the model. And key to this is a GEOS-Chem steering committee involving a number of prominent GEOS-Chem users who will take in information from their working group, in particular at the international GEOS-Chem meetings, set priorities for the model, and then work with the model support team in order to implement those priorities and review benchmarks associated with that, leading to new model version updates. And so throughout this step, we really emphasize user support and community spirit and nimble innovation. We have some tutorial videos on our own GEOS-Chem YouTube channel. If you are not familiar with GEOS-Chem, I encourage you to browse through them. Now, for the vast majority of users, GEOS-Chem is simply what we call the classic version. And that's a basic offline atmospheric chemistry model that provides you with a detailed simulation of a troposphere and stratosphere. It's driven by input meteorological data from the NASA GEOS system, and that can go to quarter-degree resolution, so that's about 25 kilometers. And we use those data to solve the chemical continuity equations for species in the atmosphere, including transport, emissions, chemistry, and deposition, with options for aerosol microphysics. The model is equipped with an adjoint for sensitivity analysis and for variational data simulation. And Devin Henze at the University of Colorado is a model adjoint scientist. Now, unbeknownst to most users is that GEOS-Chem is actually a column model. That is, it operates on columns on any grid, and on those columns it solves the local terms in the continuity equation describing chemistry, emissions, and deposition. Now, I say unbeknownst to users, in fact, the users know this, but they don't have to deal with this, because if they're simply using the GEOS-Chem classic version, then the grid will be chosen for them, and the transport will be done with our standard TV core and convection modules. But the point is that the model can operate on any model grid that is specified at runtime. And this has a number of advantages. One is that you can use any meteorological fields on any grid. You can use massively parallel simulations, and you can use GEOS-Chem as an online chemical module in weather and climate models by just pulling out this chemical module and implementing it into your weather model or your Earth system model. And we'll be talking more about this in just a minute. But first, I want to give, at this point, the floor to Randall, who is going to tell us about GCHP and some other things. Randall.
Thank you, Danielle. And as we've just been hearing, the column capability of GEOS-Chem offers this powerful opportunity for massive parallelization. And that contributes to the high performance version of GEOS-Chem known as GCHP. GCHP addresses the need for computational power to address the increasing sophistication of chemical representation with increasingly detailed chemical mechanisms such as secondary organic aerosol or halogen chemistry or size-resolved aerosol microphysics. And the model capability has been well described by documents led by Seb Eastham and most recently by Jiawei Zhuang, who has taken GCHP out to the Amazon cloud and parallelized it over 1,000 cores, setting an example of a capability that is increasingly accessible to a broad community. GCHP also offers the opportunity to conduct simulations directly on the cube-sphere grid. And this offers a more accurate representation of transport by better aligning with the parent meteorological fields produced at NASA GMAO. At the bottom, you're seeing an animation, an example animation of GCHP, full chemistry at 25-kilometer resolution, known as C360. And offering this unprecedented fine-scale structure that has been previously inaccessible to our community at the global scale. You're seeing yellow for mineral dust, blue for sea salt, green for organic aerosol, black for black carbon, and red for the sulfate nitrate ammonium system. Now, on the next slide addresses a potential concern with GCHP. And so if we switch to the next slide, yes.
Oh, I'm sorry, yeah.
Which is the grid independent capability of GEOS-Chem. So one might be concerned that with this capability to conduct global simulations at a variety of resolutions, that the natural emissions could scale with the meteorological resolution. And that dependence could then lead to an emission variability that depends upon the resolution being chosen. So this challenge has been addressed by a large community involving colleagues across MIT, University of Rochester, Dalhousie, Washington University, PKU, and Harvard University, and has created an archive of emissions at native resolution for each of the parent meteorological fields. And those emissions are now made accessible to simulations at any other resolution, thus exploiting the finest scale information available to our community for this emission structure. Now on the next slide applies these two capabilities to address another challenge or need, which is the need for a targeted fine resolution simulation over a region of interest. And this capability begins with the CubeSphere framework that you see here. And on the next slide, then refines the grid over a region of interest. This is a region of interest that can be nimbly specified at runtime with an arbitrary domain and an arbitrary resolution, leading to an equivalent of a nested capability with no additional computational effort. Grid boxes expand on the opposite face. So there is no additional, the number of grid boxes remains the same. And on the next slide then shows the effective domain that can be, or the effective two-way nesting capability that exists. There's also no need for any prior global simulations or archival of met fields. This next slide shows an example animation of the full chemistry ozone simulation over Southern California. And this region has been historically challenging to represent within GEOS-Chem due to the complexity of the topography, the complexity of the meteorology, and the complexity of the emissions. And what you're seeing here is a capability that was achieved with the equivalent of a global 2 by 2.5 degree simulation, but has a focus of a 12-kilometer resolution over Southern California, better representing the ozone chemistry within the Central Valley. You can see that resolved in the animation, and better representing the resolution of the emissions that you see in the bottom right with respect to tropomi. Now, on the topic of emissions, on the next slide then addresses an ongoing, persistent need within GEOS-Chem for consistent, timely emissions at the global scale. And Aaron McDuffie has addressed this challenge through adapting the CEDS emissions system for GEOS-Chem to update to more recent years. This is especially important over East Asia. You'll see this in the top right for SO2, this dramatic change in emissions. But as part of this effort, she's also taken advantage of the capability of CEDS to align with regional emission inventories, added in 2 new regional emission inventories to this mix: DICE Africa, thanks to Eloise Murray, as well as India, thanks to Chandra Venkataramaran. And another, as part of this effort, she's not only retained the individual sectoral information that is available in CEDS, but for the first time retained fuel type information, such that one can now conduct sensitivity simulations of the effect of ambient concentrations with respect to a particular fuel type, say, for example, coal. And with that, I'd like to turn the microphone back over to Danielle.
Randall, thank you very much. I want to elaborate a little bit on the way that we do emissions in GEOS-Chem. Eloise, I'm not able to click. Okay, thank you very much. The emission tool that we use in GEOS-Chem is called HEMCO, and it was developed by Christoph Keller back in 2014. And it's a very versatile way of handling emissions that allows you to read, combine, mask, overlay, modify emission data from a library of inventories on any grid. So if you have an inventory in NetCDF format on any grid, HEMCO will regrid it for you at the resolution of a GEOS-Chem simulation that is desired. It will do whatever you want with it, supersede some default inventory. And the important thing is that it's done with no change to the GEOS-Chem source code. So therefore, it is fairly immediate. HEMCO is so useful that we now apply it as a general data broker in GEOS-Chem. It handles all of our input data. And one thing that this has enabled in particular is custom nests defined at runtime. Randall shows this very exciting capability of a stretch grid in GCHP. But even in GEOS-Chem Classic, you can do nested simulations over any domain that you like, and simply defines this at runtime. HEMCO can also serve as an emission module for other atmospheric chemistry models. It has its own GitHub repository. It's been used for quite some time in the GEOS model at NASA to serve go-kart, its emissions relative to aerosols. And it's now also being implemented in the NCAR CESM and also in the NOAA suite of models. I would like now to turn my attention to the use of GEOS-Chem as a chemical module in weather and climate models. And here in this little cartoon, I'm showing you the implementation of GEOS-Chem as an offline model, be it Classic or GCHP. You have a GEOS-Chem chemical module solving the local terms of the continuity equations, and that is coupled with transport modules that are driven by some meteorological database, such as the GEOS assimilated met data. But the same chemical module can be used to serve chemistry updates to a weather or climate model that will do its own transport coupled to the dynamics. And of course, this is very important if you want to do coupled chemistry, climate, ecosystem simulations, but it also has a number of advantages and versatility. The important thing here is that whether GEOS-Chem is applied online, as in here, or offline, in the GEOS-Chem Classic or GCHP way, the chemical module is exactly the same. It's exactly the same code. And what that means is that the atmospheric chemistry community that likes to use the offline model because it's easy to use and contributes atmospheric chemistry updates that keeps it at the cutting edge of science, so those implementations can go into the standard GEOS-Chem model and then seamlessly pass to the weather climate model, which never falls out of date with regard to its representation of atmospheric chemistry and is always referenceable to the latest standard version of GEOS-Chem. So this has been applied for some time in the GEOS model at NASA, with which we partner quite heavily, particularly with Christoph Keller now at NASA. And Christoph has developed this GEOS composition forecast, or GEOS-CF, which is powered by GEOS-Chem atmospheric chemistry, but provides operational 5-day forecast at NASA at 25-kilometer resolution. And these forecasts are distributed through the GEOS website. You can just Google GEOS-CF and find it. This enables you to do, in particular, some near-term evaluation of GEOS-Chem. I'm trying to click here and not having a whole lot of success, but eventually I'll get it. Eloise, do you have control here? Oh, here we go. Okay, thank you very much. All right, so this is just an example for Europe, and this being Christoph, of course, he's looking at Switzerland, the station at Zurich, where you have a forecast for NO2, and you can compare to observations and essentially near real time. And so this is very useful to getting the pulse of the model, trying to understand any problems that you have in the simulation. And yeah, so this GEOS-CF capability is actually very widely used by people around the world. Let me move on to a new capability that's also mature by now, which is WRF-GC, representing the coupling of GEOS-Chem with WRF. And this has been led by Mei Fu at SUSTEC in China, who's the WRF-GC model scientist. Basically, it's replacing WRF-Chem with GEOS-Chem. So you are not touching the WRF code, you are just replacing WRF-Chem with GEOS-Chem. And the nice thing about this is that WRF and GEOS-Chem can evolve independently, advance to new versions, and that will not break the coupling between the two. We have one-way and two-way couplings that are mature. Two-way coupling means that the GEOS-Chem chemistry can modify the dynamics in WRF. And WRF-GC is now being used by a number of groups. We're using it at Harvard with my student Hai-Pei Lin, and I'm trying to click here again. And we're using it right now to simulate atmospheric chemistry during the Chorus AQ campaign. That was back in 2016. And here we're using free nests in WRF-GC, outer nest of 27 kilometer and an inner nest over Korea of 3 kilometer. And so with this, you have a simulation that extends to the global scale with the capability of GEOS-Chem, but now effectively operates also on the urban scale. All right, we're presently working in collaboration with MIT and NCAR to implement GEOS-Chem into CESM. And this is what we call CESM-GC. And that work involves a lot of heavy lifting from Seb Easton at MIT and is a cooperation with Louisa Emmons and Simon Tilmes at NCAR. So the idea here is to be able to replace the standard Mozart chemistry in CSM with GEOS-Chem chemistry. It's not like we want to kick out Mozart, we just want to provide some alternative means of doing chemistry and compare the two, which can lead to a lot of interesting science. And for GEOS-Chem users, that means that they can use their GEOS-Chem simulation in the framework of a community Earth system model, one that they can openly access. We're also providing HEMCO as an emission module in CESM that's independent of GEOS-Chem, which means that it can be used to drive Chem-Chem with Mozart chemistry. And this is an illustration of the great things that we can do with HEMCO. Randall mentioned the capability to operate GEOS-Chem on the cloud. I won't say too much about it. This was developed by Jiawei Zhuang. The GEOS-Chem Classic has been mature for some time and has been used by a number of people. It's very well supported with detailed tutorials. Randall pointed out that we can run GCHP on the cloud with over 1,000 cores, and it parallelizes extremely well. Now, chemistry parallelizes very well, so that's maybe not too surprising. But what was a real breakthrough by Jiawei is to be able to solve the multi-node communication problem on the cloud. And there's new technology available at AWS and on the other clouds as well that allows you to do this. I mean, just a few years ago, we were limited on the cloud and being able to only to use single node simulations. Multi-node communication would be very slow, but that is not the case anymore. Okay, this leads me to my final slide, which is kind of a look towards the future. What I like to say is that GEOS-Chem has one scientific base and free implementations, and that's the way it's going to continue on in the future. A chemical module that remains at the cutting edge of atmospheric chemistry, fueled by the contributions from a very large grassroots community, with very strong version control, benchmarking, traceability, and documentation. And that GEOS-Chem chemical module then serves three types of applications. The GEOS-Chem Classic application, that's basically our basic service, and that is not going away because there's considerable demand for a simple tool to be able to do atmospheric chemistry modeling on global to regional scales. We're going to continue, of course, supporting GCHP, and Randall is a GCHP model scientist in addition to his general co-model scientist hat. That enables, of course, high resolution simulation with MPI, more accurate transport. And Devin Henze is presently developing an adjoint for GCHP. And finally, GEOS-Chem in weather climate models. I think this is going to be an increasing application, both to be able to do geochemistry ecosystem coupling, climate coupling, and be able to address a wide range of interesting questions at the interface between fields, but also, as I showed you with WRF GC, being able to access any meteorology and resolution. So with this, I want to thank you very much for your attention, and I'll be happy to take any questions. And Randall, I'm sure, will be happy as well.
That's great. Thank you, Danielle. Thank you, Randall, for a really very interesting, so very impressive technical innovations you've presented. I'll open the questioning. I know that Eloise also has some questions. So you touched on, I mean, some of these innovations will have implications for the kind of computing resources needed to run GEOS-Chem. Now, I was particularly taken by the stretch grid model. That's very attractive for a number of reasons. You mentioned later on that the model is very highly parallelized and works fairly well over 1,000 nodes. Is that exclusively just for the Amazon setup, or have you managed to run that at Harvard with those, or in Washington, University of Washington, with those number of nodes? I was just curious whether we'd have to move towards GPU tech as as the resources needed?
Randall, you want to handle it?
Sure. So we have been run GCHP on Compute Canada on 864 cores. That was what was available to us at the time. And we have not had a need or utility for any GPU components to this capability. Rather, it's been all CPU based. Moving forward, I don't foresee any need for any specialized GPU infrastructure, but rather our targets are traditional CPU infrastructure at this time. But that would be something to explore, which is a GPU capability, but that's really separate from what we're doing here.
Okay, thank you. Eloise, did you have a question?
Yeah, the AWS capability sounds really great because it gives people the opportunity to use GEOS-Chem where they don't have local facilities to accommodate it. Is that the case, or is it still quite expensive to use? And I think of, my students, African students who will go back and want to use GEOS-Chem. Is this available to them, or is the exchange rate just not favorable?
Yeah, thank you for that question. The use of GEOS-Chem Classic is really relatively cheap, and there's cost numbers in Jiawei's paper. GCHP run with over 1,000 cores gets expensive pretty quickly. And I think this is something that funding agencies are going to have to figure out very soon, is that they don't presently have a good cost model to support researchers using the cloud. There's efforts, at least in the US, that I'm aware of, but they're still pretty timid. And yet, it's an obvious solution to our computing problems, to be able to use the clouds and to be able to charge us to our grants. At present, our computing at universities or in government labs is heavily subsidized. So we often don't see the cost, or we only see a fraction of the cost. But if you look at the full cost of computing, the cloud is very competitive, which is why private industry has been more at the forefront of using the cloud than universities or government labs. Somehow this is going to have to change. But, and so at this point, I would say running GCHP on the cloud, I would use it for testing, but for long simulations, you better have a thick wallet. But GEOS-Chem Classic simulations, no problem. Users who are only occasionally use GEOS-Chem, it's very advantageous to use a cloud.
Great, thank you. I have one more question, just out of curiosity. I know we have to move on to the next talk, but I couldn't resist it. So the stretch grid, I mean, is there any issues with discontinuities in, say, radical chemistry? How do you minimize that effect as you decrease the size of, progressively decrease the size of the grid?
Yeah, thanks, Paul. Indeed, I think one of the attributes of the stretch grid is that there is no discontinuity, that it is a smooth transition in the resolution of the grid from the domain of interest to the exterior domain. And that is an advantage over the traditional fixed grid that we have had with a clear discontinuity between the global background and the nested domain. Regarding radical chemistry, I don't foresee any specific issues. I should say that there is a need to better probe the boundaries of the stretched grid. So for example, one could coarsen the background grid at the global scale to coarser resolutions than we've traditionally explored with GEOS-Chem, and that might lead to suffering in the chemistry that propagates into the nested domain. So we have to be cautious of exploring that capability, but in a general sense, I think it's advantageous with the absence of those discontinuities.
Okay, thanks. Anyway, it looks fantastic, so I look forward to being able to use that very soon. Okay, so we're going to move on to our, thank you again to Danielle and Randall for the keynote talk. We're now going to move on to the science talk session 2. Our first speaker is Ryan Pound. Ryan, I will give you a quick heads up when you've got 30 seconds to go. Okay, over to you. We can't hear you. Ryan, can you unmute?
Hello?
Hello, go for it.
Hi. Yes, my Zoom's just crashed. It's currently restarting.
Okay.
You might want to skip.
Yeah, okay. So what we'll do is we'll go to the next speaker. We'll come back to you, Ryan. So the next one is Zhao Chen?
Yeah, I'm here.
Okay. Are you ready?
Yes.
Okay. Eloise, I'm sorry, I have to drop you in it. Okay. All right, so once you've taken ownership of the slides, you can start. Okay.
I'm trying to click.
Okay, it takes a few seconds, so just click it once and wait. So if you've got permission, just go for it.
Yeah, I have the permission.
You do or you don't?
I have.
You have, okay. Okay, I'll start.
Hello, everyone. I will talk about the estimates of Southern Ocean carbon fluxes using atmosphere inverse analysis. This work is part of the project SOLATA, Southern Ocean Optimal Approach to assess the carbon state, variability, and climatic drivers. Since 2001, the distribution of the atmosphere pressure system became more asymmetric. This leads to the changes in the temperature and the circulation in the ocean, and then leads to the changes in the surface partial pressure of CO2 anomaly, delta PCO2. The observation of PCO2 is one way to calculate the ocean carbon fluxes. This figure shows the decadal trends in the ocean carbon sink. 3 different colors represent the products from 3 different methods. The orange one represents the ocean fluxes based on the PCO2 method. The yellow one represents the products from ocean inversions. The purple one represents the products from ocean biochemistry models. Positive values represent the decrease in sink, and the negative values represent the increase in sink. These 3 methods almost agree that there was a weakening trend in 1990s and a strengthening trend in 2000s in the global ocean and Southern Ocean carbon fluxes. In this study, we will investigate the variation of the Southern Ocean carbon fluxes from atmosphere inversions. Atmosphere inversions offer a method to find the optimal carbon fluxes by comparing the model CO2 and the observed CO2 concentrations. The simulation is based on the prior carbon fluxes and the transport model GEOS-Chem. The data assimilation method is LETKF, local ensemble transform Kalman filter. In this study, GEOS-Chem version we are using is V11. Meteorological fields are mirror 2. Spatial resolution is 2 by 2.5. We use the prior land fluxes from process-based model GEOS. We use the PCO2-based products from Land-Schuster as our prior ocean fluxes. To improve the estimates of ocean fluxes, we develop a spread-based uncertainty scheme to specify the prior ocean uncertainty. The CO2 observations come from NOAA OPSPEC data. So I can't move to the next slide. Oh, okay. The spread-based uncertainty is to calculate the ensemble spread based on multiple prior ocean fluxes for each grid. In this study, we use 3 different prior ocean fluxes. When the multiple prior ocean fluxes agree each other, the uncertainty is small, which leads to a tighter constraint on the prior ocean fluxes. Then the posterior fluxes were close to the prior. It is helpful when there is not enough CO2 observations in the ocean region. When the multiple prior ocean fluxes are not consistent, there is a large spread uncertainty, which allows the estimates impacted more by the observation in this region. This figure shows our estimates for a long period. The red line and the shaded area represent our posterior ensemble mean and uncertainty. The black dotted line is our prior. From 2000 to 2012, both products show significant increased uptake, which are consistent with previous studies. This figure also shows the uptake is decreasing from 2012 to 2017. We are comparing our results with other inverse systems results. The yellow one represents other inverse system CHEM's results. Their trend is similar to our results. A significant increase of uptake during 2000 to 2012 and a decreased sink during 2012 to 2017. The other 2 atmosphere inversion products, Carbon Tracker, the pink one, and the Carbon Tracker Europe, the blue one, both of them have a smaller trend during the first 13 years and show a different trend since 2012. One main reason is that CHEMS and our study use the same prior ocean fluxes, and Carbon Tracker and Carbon Tracker Europe, they use other prior ocean fluxes. Comparing the 4 atmosphere inversions, the difference of idle mean reaches about 0.9 picogram per year for some years. This comparison shows the estimates of Southern Ocean CO2 fluxes from atmosphere inversion are largely dependent on their respective prior ocean fluxes and are sensitive to the model parameters. So this figure shows the comparison of Southern Ocean CO2 fluxes from different methods. The red color represents the atmosphere inversion group. The blue color represents the observation PCO2-based group. The purple color represents the ocean model group. Each symbol represents the individual products. The circle and the arrow bar represents the ensemble mean and the spread uncertainty of each group. From the first row, the long-term ensemble mean from 3 groups agree well is about minus 1.3 picogram per year. From the second row, the ensemble mean of the inter-area variability from atmosphere inversions and the PCO2 groups are much larger than the ocean model groups. From the third row, the trends from ocean models are much smaller than the other 2 groups. Except the widely used observations from NOAA, we have additional daily CO2 measurements at the Halley Station in the Southern Ocean region from BAS with the support of the project of Solata. This daily CO2 is available from 2013 to 2016. Now we are focusing on the incorporation of high temperature resolution measurements into the inverse system. Finally, the summary. The estimates from GEOS-Chem LETKF shows a significant increase in uptake during 2000 to 2012, and the uptake is decreasing during 2012 to 2017. For the future's work, we are planning to incorporate more high temperature resolution CO2 observations. We also plan to extend the spread-based uncertainty scheme by incorporating more prior ocean CO2 fluxes. So that's my presentation. Thank you.
Great, thank you very much. One quick question. So why did it suddenly change in 2012? What is any physical reason why there was a dip and then it came back up again?
So maybe not exactly 2012. So for 10 years, decade change. So the basic reason, possibly because of the atmosphere pressure system trend changes in decade.
Okay, great. I have one question from Matt, and he was asking about processes that are missing in the current representation of CO2 in GEOS-Chem. Are you worried that you have all the processes which could describe allow you to interpret the atmospheric data in terms of ocean uptake?
For a GEOS-Chem, GEOS-Chem, now is a lot ocean process. So we just have we just use the transport in the atmosphere.
Yeah.
So the ocean fluxes is the same as the land fluxes and then mixed in the atmosphere.
Yeah.
So that's the challenge to estimate the ocean CO2 fluxes.
Indeed. Yeah. Okay. Thank you very much. We're going to return to the first speaker, Ryan. Ryan's got his Zoom session set up again. So Ryan, are you there?
Hello, yes, I'm here. Sorry about that.
No, but it happens. So start whenever you're ready, or like now.
Hi, so I'm Ryan, and I'm going to be talking about the impact of model resolution in terms of spatial resolution for over remote marine environments. So the importance of spatial resolution over cities is well known, and choosing the right resolution is very key if you want to represent these regions. However, it's widely considered that in more remote environments, such as the remote marine environment, model resolution plays much less of a controlling factor. So we're going to evaluate the importance of resolution in remote marine environments and the transition from land into these areas. So we're going to start. Yeah. So I'm going to briefly talk about the model setup. So we focus on the tropical Atlantic, specifically around Cape Verde. We create a flex grid nested region and can run all of the model resolutions shown. However, today we're just going to be showing from 4x5 down to half a degree. We've studied Cape Verde because at York we have been running long-term measurements of background clean air at Cape Verde Atmospheric Observatory. So this acts as an area which we understand well and we have used in the past to evaluate model performance as a whole. And to reduce any excess factors from the inputs, we have decided to use the same boundary conditions, met fields, time steps, and output frequency to control for those factors. So to start off with, we're going to look at surface propene. So as we can see here, going from 4x5, of course, this resolution in the top left down to the bottom right, we can see that as you increase the resolution, you can resolve plumes, ship tracks much more clearly. This isn't much of a surprise because as you increase resolution, you will be able to capture these. So this isn't necessarily the best measure for working out how to understand the differences between the resolutions. Instead, we can look at the time series from the perspective of Cape Verde Atmospheric Observatory. This is now much clearer, starting to show that there is a distinct difference between the resolutions. And based off of this time series, you would draw very different conclusions about the model performance. If you used to compare this to our observations based off of different resolutions, you would get a different answer of how well your model is performing. Another way we can think of the the differences between the resolutions across this grid is to take slices of latitude and longitude represented by the red lines drawn on the half a degree map there. And taking these constant slices, we can see from south to north on the left and from east to west on the right, the effect that this has as you go over the structure of this region. So as we go from the South Atlantic up across the islands and then back down to the north, you can see that there is the coarser resolutions are depicting that local island spike in a very different way to the finer resolutions. And again, on the right hand side, going across from Africa over the islands to the remote Atlantic, you can see that it's not that the gradients as you change from these regions is definitely affected by the model resolution. And finally, we can think of the difference between the resolutions themselves. So here we have the percentage difference between 4x5 and half a degree. We regrid the half a degree onto 4x5 for the comparison. As you can see here, as with all of the other plots, it's just another way of visualizing that percentage difference between the model resolutions. So this isn't just a picture of having a higher resolution creates a need to map for the plumes. There is a distinct difference between what the model is predicting based on what resolutions you're looking at in this environment. Of course, there could be many controlling factors which can contribute to this. So to do this, we create some very simple idealized tracers. These idealized tracers have no source within the grid, so there's no emissions, and they only come from the boundary conditions, which are constant throughout time. The very first of these simple idealized tracers has an infinite lifetime, and no other factors can control it. So this is simply just blown in from those boundary conditions until it reaches an equilibrium in the grid. And as you can see here, whilst the different resolutions take a different path to reach that equilibrium with the boundary conditions, ultimately they all have a very similar result of about after 1 month of running at this time series from Cape Verde, we see that 1 ppb constant with the boundary conditions. So to expand from this infinite lifetime tracer, we can now look at a tracer which is simple but now has a lifetime of 1 day. So this is going to start to show us some information about what's happening in terms of the chemistry. So as you can see here, this is where we now develop the differences. This simple tracer now has differences between the resolutions, and there is one last tracer we can go to, which is now a idealized wet deposition tracer. So this now is what is wet depositing like HNO3, but everything else is the same. There are no emissions within the grid, and the only source is from those constant boundary conditions. As you can see here, this is something where we start to see some unexpected behavior. It's, whilst we aren't particularly expert when it comes to wet deposition in a model, it's our understanding that we shouldn't, if there is no source within the grid of any tracer, you should not be able to create any more of it. So as you can see here, the wet dep species is oscillating as you would do and having differences between the resolutions, but at key times shown by the arrows on that time series, you can see that the wet deposition inside the grid at our chosen point is exceeding the source from the boundary conditions. So this is a bit of a mystery to us at the moment and is currently an open issue on GitHub. A shameless plug for myself here, so if anybody wants to come and have a chat about this and work out maybe what's going on, I'll be more than welcome to your input. So just to summarize, there is a resolution impact in specifically this remote marine environment and probably others. And just because a site or location is remote on the map doesn't necessarily mean it is remote if you start to consider model resolutions. This resolution dependence will impact your conclusions about model performance, especially when you're using sites such as this. we use idealized tracers to explore possible causes of this and have already stumbled across something which in wet depth we think is showing some unexpected behavior. Thank you very much for listening.
Great, thank you very much, Ryan. We have a question from Danielle. So can you relate differences between resolutions to shear-driven numerical diffusion? Do you also see non-linearity in chemistry?
So we're exploring the aspects of the chemistry with the idealized tracers. So this is still something that we're working on, but we're trying to work out if this is, yes, something that exists within the chemistry, so such as the differences in that 1 day tracer lifetime. Is that something that's coming from the, is this something that's coming from the chemistry, or is this something that's coming from something else to do with how it's being transported and mixed across these grid cells? I think that was the question, wasn't it? And did you repeat the first part of that question for me?
Can you relate differences between resolutions to shear-driven numerical diffusion?
Yeah, so that's something else that we are investigating and working out the best way to do it, and we're hoping that further study using these idealized simple tracers to really pinpoint what's happening in terms of the different aspects of model, but let's say to be continued part of the story.
That's great. Thank you, Ryan. We're going to move on to the next speaker, who is Mark Lunt from Edinburgh. Mark, you ready?
I am, yeah.
Just need to put your presentation up. Okay, where you go.
Okay, cool. Well, thanks, Paul. So I'm going to talk today just briefly about some work we're doing over the last year or so using nested grid simulations with GEOS-Chem to look at methane emissions. And I guess what I'm going to talk about today is a very brief overview in the sort of limited time I got. But yeah, feel if you want more details or anything, please engage in the sort of in the chat afterwards, or contact me on that email address that's shown. So I think I'm the first of 4 or 5 speakers to be talking about methane. So this plot might, or similar plots might appear quite a lot, but apologies to speakers coming after me if I'm stealing your thunder. So this is kind of where a lot of methane research is framed, looking at this global growth of methane, particularly since the mid-2000s. So this record is the globally averaged NOAA surface record. And what we see is that we have this sort of flattening in during sort of 2000, 2006, and then a rise since. And there's lots of research to why we methane's increasing, and the changes in emissions or the change in sinks that are causing it. And it's a bit of an unconstrained problem, but one of the important sources of data for this is satellite data, which can really start to tell us where change is occurring. And there's been a number of papers recently about this. And this plot here is from one of them, from Scott Miller and others from last year, which is looking at the trends in GEOSAT data between 2010 and 2015. And was the sort of growth trend anomaly. So the anomaly from that global growth rate that's shown on the left. And basically it's highlighting that the GEOSAT data seems to be showing increases in China and India, and also in the tropics in Africa. And so what we've been doing particularly is try and interrogate these sorts of changes in more detail. So we've been doing this in a sort of regional study, using nested simulations, like I say, and there are sort of many reasons. So the plot here just shows the sort of global output that's come from one of Brian Marsek's papers from last year, which again shows that sort of similar pattern. This is from doing methane inversions, but with regional inversions, we can start to maybe explore things in more detail. So I'm going to focus particularly on Africa. And so within the changes that he shows here, can we actually sort of start to interrogate that in more detail and look really what's causing those changes. And then also, potentially, we see that a number of papers have mentioned biases in the GEOS-Chem simulations of methane, particularly due to stratospheric transport. But the advantage of having a regional simulation is that you can sort of negate those by scaling your boundary conditions to these regional simulations to fit the data, so that they're not unconstrained, and so you're less affected by these sorts of biases. But then also, I'm just going to touch briefly at the end as well about some sort of flight campaign data that I've been working with, where of course you only might have a very limited set of data. So this is some work we're doing with colleagues at Royal Holloway, University in London, and the British Antarctic Survey, where strangely Antarctica moved to the Amazon, but looking at some data that we have over Bolivia. So in terms of actually operating these the methane nested grid simulations, well, as Danielle alluded to earlier, it's very straightforward to run. Especially with the HEMCO setup these days, you can create any nested grid in anywhere. The only thing that it does need changing is with this, that's hard coded into the tag methane simulation, is the soil absorption. And it has its sort of weird features that it has to be the 50-inch tracer. So this is something I've sort of adapted for needs to get rid of, because it affects, if you don't want that to be the case, you need to change it. But it'd be good to build that into a more general user version. So if anyone else is working on that, it'd be good to hear, but otherwise it'd be, that's something I'd like to sort of give back, as it were, as part of the GEOS-Chem community, is to make it more general so you don't have to go into the code and hard change it. But other than that, it's very straightforward to use. So I'm going to jump straight into some results here because I don't have too much time. So this is plots from a paper that we published last year looking at methane from Africa between 2010 and 2016 using data from GEOS satellite. And basically what we see here is on the plot on the right is this orange line. We see this increase in emissions from East Africa, which is depicted in the left for the countries that are bordered in, with this same orange color. And a lot of this we attributed to changes in hydrology from this wetland called the Sud in South Sudan, where this seems to be an increase in wetland extent over this period. And so this sort of detail that we're able to get from these nested simulations, which it doesn't really tend to come up out of these global inversions, just generally to do with the resolution of both the data and the priors, where the Congo Basin tends to be much more prominent at the course of global resolution. So another useful sort of feature of nested resolutions, nested grid simulations, is that you can sort of start to extract what the background component of the data is versus what the emissions component of the data. So here, just showing us where we've done a simulation over this domain over Africa, and what I've done is run this using the boundary conditions generated by the global model run, and then without any emissions within the domain, and then subtracting that from the satellite data, and that allows you to see essentially the emissions component of the data. And with the GEOS data, it's fairly sparse. It's quite hard to work out what's going on. But of course, over the last couple of years, we've had data from the propene satellite, and now we can start to see in much finer detail where these sorts of regions of emissions are. And particularly, you can pick out this area in South Sudan where we have this big wetland. And so we've been using these propane data recently to look at changes over the last couple of years, particularly in wet seasons. So this is again showing these enhancements where we've subtracted the model background over East Africa. And particularly what we're saying in the bottom right figure here is really large enhancements in October, November, December of 2019. And this is one of the main rain seasons in East Africa. When we feed this into, this is quite a big step, but feed it into some methane inversions, then we generate this time series of emissions, and we see particularly this big spike in emissions in this rain. The grey bars depict the rainy seasons. And what we see here is a big spike in this rain season at the end of 2019, also at the beginning of 2018, and much less in the intermediate seasons. And then finally, I thought I'd just touch on some other work we've been doing in looking at methane in Bolivia. And this is a really limited data set that we have here. Like I say, so this is courtesy of James France at Royal Holloway. So where they've taken this plane and just flown a few days over what's called the Flanos de Moxos wetlands in Bolivia. And so just a few results which is plotting here. So the top panel just shows the observations that we have from these flights. Shown with these circles. The blue line down the middle is the main river channel. And basically what we see is we get this big, we can infer the sort of large emissions that follow the course of this river channel. And these turn out to be really quite large emissions, seem to be even larger than those that you get in the centre of the Amazon. And this is just confirmed some sort of box modelling we've done as well, which finds the same thing. So with that, I will just leave up some summaries that, that these regional versions are really useful for interrogating the changes that we see in the global methane budget, and it's really useful to have this feature within GEOS-Chem, and certainly it's allowed us to identify this influence of East Africa on global methane, and then we can also identify these sort of other important sources that previously probably haven't been able to see. So thank you.
Thanks, Mark. We have a couple of questions. One is from Eloise. Trends look contradictory in Africa from the two studies that you mentioned earlier in your talk. Isn't this cause for concern? Might be exploring trends that aren't robust. I think that was Scott Turner and the other study.
Not sure what by contradictory. It might be that if it's that those numbers don't agree, it's because they're defined over different areas.
Oh no, I think it's the spatial distribution. I think it's slide 3.
Oh, sorry, compared to what Braham's paper shows.
Yes.
Yeah, so this is, I think, the issue with potentially the issue with resolution. So that if the data is that's using the 4 by or 2 by 2.5 model or the 4 by 5 model, and then also within the prior emissions data set that we use, the Congo Basin is really dominant within that, and so at those coarser resolutions, then it sort of swamps the signal. I think that you get at the finer resolutions. So that's the reason I think why you get the different spatial patterns. But would need to check.
Sorry, I'll let you finish. What did you say?
No, that's fine.
Okay, so the next question was Danielle. We found Tropome to have observing problems for wetlands because of clouds, not a problem in Africa, ?
Yeah, I've done a lot of filtering of the data beyond what they sort of, I think they're very optimistic in terms of the data that they can use, and we're working quite closely with the Tropome data team as well. There is obviously an observing bias in terms of at the height of the wet season where it's going to, well, not necessarily, but the height when it's rainy, it's obviously going to be cloudy. But I think, yeah, I think a lot of filtering of data is needed beyond, and we've been comparing quite closely with the result with GEOS-Sat as well, and using that essentially as a cross validation to ensure that we get consistent results between the two.
Okay. Great, thanks, Mark. We'll just move on to the next speaker, Xiao Lu from Harvard, who's going to be talking about a similar subject, global methane budget and trends in 2010 to 2017.
Yeah, thanks, Mark. Can you hear me?
Yes, go for it.
Okay. Hi, everyone. I'm Xiao Lu from Harvard. I'm going to talk about global methane budget and trends in 2010 to 2017, emerged from in-situ and set observations. And before I start, I would like to thank my colleagues from Harvard, NOAA, JPL, and University of Leicester. Our community has been working hard to understand the methane budget and trends. Yeah, here we go. So methane has a wide range of anthropogenic and natural emissions, but the attributions remain highly uncertain. And the recent methane regrowth has been puzzling us a lot, as also shown in the previous talk. A general approach to optimize our methane budget estimate is to use methane observations in immersion modeling, as also introduced in previous talk. We typically have two kinds of observations in methane immersion. The first one is in-situ observations. So here I'm showing you the OSPAD dataset developed by NOAA, which includes global extensive in-situ observations from surface towers, shipboard, and aircraft. And these in-situ observations are accurate and sensitive to surface flux, but it's very sparse on the global scale. We also have the satellite observations. So here I'm showing you the atmospheric methane column retrieved from the satellite, GEOS-Sat satellite. These satellite observations are massive and has global coverage, but tend to have larger error associated with the retrieval. And one important question that has not been answered before is whether the in-situ and satellite observations are consistent and complementary in immersion. And the answer to this question will benefit the design of the future methane observation system to make use of observations to get our best estimate. And we are going to answer this question using analytical inversion. So we will use OSPAD and GEOS-Chem as the observation constraints. The state vectors in our inverse modeling is defined as the methane emissions and trends on the 4x5 model grid as well over the 2010 to 2017, as well as the OH concentrations as an estimate of the methane loss. And because wetland emissions has shown seasonal and interannual variability, we separately optimize the monthly mean values in 14 subcontinental regions. And our prior estimates are from the bottom-up inventory that represent our best knowledge at present. We use the chemical transport model to as the forward model to link the state vectors and observations. And the inversion is done analytically, which means that we will directly construct the Jacobian matrix, and the inversion will yield closed form posterior error covariance as well as the averaging kernel sensitivities. And we will conduct 3 inversions. The first one will only use OSPAD as the observation constraint. The second one will only use GEOS-Chem, and the third one jointly use GEOS-Chem and OSPAD. An important question is how to properly weight the institute and set observations in the inversion. I'm not going to the detail of this slide, but the basic idea here is that we introduce a regularization parameter gamma in the cost function. And by comparing the parameter term and observation term in the cost function with different choice of the gamma value, we find that for institute observations, we don't need any regularization. But for GEOS-Chem, we need to weigh down the observations to avoid overfitting. And this parameter is also applied in the joint inversion to weight different observations in the inversion. And we now compare the ability we now evaluate the posterior model fit to the observations. So here I'm showing you the prior model bias compared to the OSPAD on the top and GEOS-Chem in the bottom. We can see at the initial state, our model shows no bias compared to observations, but we assume there's no trend in the prior emission, we will have a negative trend growing with time. And the second and third column here shows the result from the OSPAD and GEOS-Chem only inversion. We can see the OSPAD inversion will fit both of the OSPAD and GEOS-Chem observation. So it means that even though the OSPAD institute observations are sparse on the global scale, it has no problem to constrain the background methane as well as the methane budget imbalance. However, the GEOS-Chem inversion still show large bias compared to the OSPAD observation, especially in the northern mid-latitudes where we have large methane emissions. The fourth column here shows the result from the joint inversion. And we find that the joint inversion in general provides the best fit to both of the OSPAD and GEOS-Chem observation. So it indicates a benefit by having both of them in the global inversion. We now compare the ability of OSPAD and GEOS-Chem to constrain the methane anthropogenic emissions. So here I'm showing you the averaging kernel sensitivities as well as the DOFs from different inversions. We can see globally, GEOS-Chem will provide more information than OSPAD because it provides a global coverage of the data. But adding OSPAD to GEOS-Chem inversion can add 50 independent pieces of information or DOFs to the inversion. So this reflects the complementarity between these two data sources in the inversion. If we look at the spatial patterns, we can see GEOS-Chem provide important message over the tropics, but OSPAD can be much more variable in the northern mid-latitudes where we have very dense institute observations. We now compare the posterior corrections to our prior anthropogenic emissions. We can see there are many consistencies between the OSPAD and GEOS-Chem inversion. For example, they agree well on the downward correction of methane emissions over China and over Europe. In US, all inversions suggest that the prior emissions are too low, but the spatial patterns is not very consistent. The joint inversion will combine the information from the two, but mostly follows the result from the OSPAD because it shows higher averaging kernel sensitivities over the US. We also see that the OSPAD provides variable information over Canada, which is not detected in the satellite-only inversion. And now let's move to the anthropogenic emission trends. So here I'm showing you the trends estimate from different inversions. Again, by comparing the DOFs, we can see the GEOS-Chem provides more information than OSPAD on the global scale, but OSPAD can be more important in the northern mid-latitudes. the spatial patterns of the estimate trends are not very consistent between the inversions. And the joint inversion mostly follows the result from GEOS-Chem because it provides a much higher depths. But importantly, all inversions suggest that the anthropogenic emissions on a global scale has been increasing from 2010 to 2017. And before the last slide, before conclusion, let's sum up to look at the global methane budget. Here we can see that all inversions suggest different absolute values of the methane source and sinks, but they agree very well on the methane imbalance of about 25 telegram per year. And this methane imbalance is equivalent to the methane mean growth rate of about 8 ppb per year, which is comparable to the observation. The joint inversion
suggests 30 seconds.
Thanks. The joint inversion suggests a total source of 551 and loss of 528 telegram, which is consistent with the carbon project. One more thing here is that we found having OSPAC in the joint in the inversion helps to lower the error correlation between the methane emissions and methane loss in the inversion. And this is because the OSPAC inversions are more sensitive to the surface flux, so it can better distinguish the methane change from emissions and to the loss. So here comes my conclusion. I think I'm running out of time, so I would like to stop here and take any questions you may have. Thank you very much for attention.
Great, thank you very much. I had a question from Eloise. So you've used so OBSPACS has been used to infer methane fluxes. Have you evaluated the a posteriori fluxes concentrations using, say, TCON or some of the aircraft data? So it could be HIPPO, or it could be ATOM, or anything that would, you know, provide a useful test to this. And you've already shown it, have you? No, good.
Yeah, we haven't do that here, but I think if we use OSPAC in the inversion and compare it with the GEOS-Chem observation, it already provides an independent evaluation by using OSPAC. We haven't used TCON in this study to evaluate the posterior model fit.
Oh, sorry, could you just repeat that a minute? So OBSPAC is it's a collection of in situ data, right, with the aircraft and the ground. Okay.
Yeah. Yeah.
But you've inferred fluxes from that. So, but then you're comparing the.
Yeah. So the OSPAC observation includes measurements from surface, tower, shipboard, and aircraft, and we indeed use all of them in the inversion to inverse the methane flux. But indeed, the surface observations will provide a stronger power to construct the surface methane flux.
Okay, thank you.
Answer the question? Yeah.
Yeah, I have another question, but I'll do it via the chat. There's another question here from Amir Suri. To what extent do errors in vertical diffusion impact your inversion? Did you propagate the model parameter error, such as PBL, to the posterior error?
Yeah, so any error in the model error will indeed propagate to our estimate, but we haven't explored a lot in this aspect, but we have, I think we have a lot of previous work using GEOS-Chem as a forward chemical transport model, as a forward model to do this inversion. Yeah, I think I don't have a quick answer on my mind, and how much will these errors propagate to our posterior estimate. Yeah.
Last question, because we've got one from on the chat room, the question and answer session from Nadine Unger. How well do we understand the soil sink of methane? How does that impact your analyses? Seems like a lot of mathematical work for basically a lot of maths for small tweaks in the budget. So, you know, how well do you think you've captured some of the minor processes which drive the methane budget?
Yeah, so the sink from soil is not optimized in this inversion, and I think from our prior estimate, I think the sink is about 30 or some telegram per year, I guess. So we haven't optimized that inversion, but it's a minor sink. Yeah. Okay,
great. Thank you very much. The next speaker is Zen Q from Harvard, and they will be talking about the methane budget, global methane budget constrained with tropome. Are you ready? We can't hear you.
Okay.
Okay, ready?
Yeah, I can, okay, I can click on this. Okay, so hello everyone. Today I'm gonna present on the global distribution of methane emissions from Chopolmy inversion. So methane is the second most important anthropogenic greenhouse gases. The climate action requires quantification of its budget, but this is rather elusive. Anthropogenic sources contribute to a large portion of methane budget. Wetland is the largest natural source, and methane is the major sink. The recent launch of Chopolmy provides unprecedented high resolution and daily coverage of methane concentrations, as can be seen in the comparison with GEOS-Chem on the left-hand side. Sorry, this is. Yeah, so Chopolmy has a footprint of 7 by 7 kilometers when it was launched, and this has been reduced to 5.6 by 7 kilometers recently. The absorption of sunlight in the reflected radiances allows for the retrieval of methane abundance using a full physics method. However, the success rate is only 4% due to the impact from cloud and surface albedo. We use GEOS-Chem version 12 to perform global simulations of methane at 2 by 2.5 degree resolutions for the whole year of 2019. The map on the left-hand side shows our prior emissions. It represents our best understanding of methane sources. The initial condition on January 1st is scaled to match Chopolmy, and we do not perform stratospheric corrections due to the smaller biases at this resolution and over low latitude regions, as pointed out by Stanovich et al. We therefore excluded high latitude regions poleward of 60 degrees from our inversion. So here we compare Chopolmy and GEOS-Chem methane observations using GEOS-Chem as a platform so that we can eliminate the impact from a priori and averaging kernel. The differences between Chopolmy and GEOS-Chem are stable across the seasons. Their absolute values are all smaller than 2.5 ppb. So we only show the results from spring here. The systematic error between Chopolmy and GEOS-Chem reflects the variations of their spatial distribution and have values around 10 ppb for all of the seasons. So we expect some differences between Chopolmy and GEOS-Chem inversions. However, this systematic error is at the 10 ppb threshold pointed out in Butchewitz et al., meaning that we can still get reasonable and comparable results. We also compare Chopolmy and GEOS-Chem observations with ground-based TCOM measurements. On a global scale, both of them are unbiased with biases smaller than 1 ppb for both of them. The 2 points with large discrepancies are over high altitude regions and are not focused in our study. The systematic error is 11 ppb for Chopolmy and 6 ppb for GEOS-Chem, showing that the larger standard deviations in the spatial distributions of Chopolmy compared to TCOM measurements. But this is still close to the 10 ppb threshold. These evaluations demonstrate the appropriateness of using Chopolmy observations to perform methane inversion. In our inversion, we have 40-20 elements for annual non-wetland emissions, and we also optimize monthly wetland emissions over 14 regions and annual hemispheric OH concentrations. So this is similar state vectors at what Xiaolu just presented, except for we have higher resolutions for non-wetland emissions. The Jacobian matrix K here describes the sensitivity of methane column mixing ratio to the state vector. And we assimilate each individual's Chopolmy observations. And together we have 56 million observations in 2019. The observational error covariance matrix is diagonal. Its diagonal elements are the sum of instrument representation and modal errors. And the prior error covariance matrix assumes 50% errors for non-wetland emissions, 10% errors for OH concentrations. Both of them do not have error correlations. And we use the ensemble model outputs from Y charts for the errors of wetland emissions. It has both spatial and temporal correlations. Using these variables, we can define a cost function J and we search for its minimum using analytical solutions. The regularization parameter gamma here accounts for the effect of error correlation not shown in the observational error covariance matrix. We use a value of 0.002 here. It is rather small because there are large error correlations between densely distributed high-resolution CHOP-OMI observations at the 2 by 2.5 model grid cells. The analytical inversion enables us to calculate the averaging kernel sensitivities, which measure the capability of the observation system to constrain the state factor. In our study, the averaging kernel are generally higher in East China, India, Middle East, and the United States, meaning that these regions are most responsive to the inversion. Here we show the differences between GEOS-Chem and CHOP-OMI before and after the inversion. The inversion successfully reduced the negative biases over West US, Africa, Middle East, and India, and the global cost function has reduced by 48%. This all demonstrates the capability of CHOP-OMI to perform a successful inversion. So here we compare the emission scaling factors from CHOP-OMI inversion on the left-hand side with GOSAT inversion over 2010 to 2017 from Xiaolu's study. Both inversions show consistent overestimates of Edgar emissions over North China Plain due to the overestimates of emission factor from coal productions. They also have upward adjustments in oil and gas production regions, for instance, over Texas and Middle East, suggesting higher leakage rate than the bottom-up estimates. The two inversions have different results over Amazon and Southeast China. CHOP-OMI has smaller corrections over Amazon due to its low retrieval success rate over cloudy regions, and the different changing directions over Southeast China can be explained by the mismatch of seasonality of methane rise emissions and the number of CHOP-OMI observations.
You have 30 seconds.
Okay, thanks. Rice emission is the dominant source of methane in this region. However, during the summer, when rice emissions are high, only a few observations are available in this region. So emission adjusts to match CHOP-OMI observations in the surrounding regions in CHOP-OMI inversion, leading to different results from the GOSAT inversion. So I'll leave you with the summary and I would be happy to take any question. Thank you.
Great, thank you. I have a question here from Eloise. So this is for non-experts in the webinar. Why is CHOP-OMI data limited to land? Have you used data that might be collected over the ocean? Is there any sensitivity to methane to measure its collected?
Yeah, I think it is related to the retrieval algorithm in CHOP-OMI, which is different from the one for GOSAT, so that it doesn't have any observations over ocean. I'm trying to go to the one that shows the comparison.
Okay, that's great. That's just curiosity. Great, thank you very much. There are no other questions. We'll move on to the next speaker, who is Shuying Yu from University of Minnesota. And they're going to be talking about multi-inversion framework for upper Midwest methane sources. Are you ready? Hello?
Hello, I'm here.
Hi, okay, so the floor's yours. Ready, just whenever you're... Are you ready?
Yep, thank you.
Okay. Remember, there's a delay in the slide transition.
Yeah. So hi everyone, I'm Jane from the University of Minnesota. I would like to present our recent research about methane emissions in the Midwest, constraints based on aircraft inversions. This aircraft measurement was from the GEM project. And this study is currently in ACP discussion. We would very much appreciate if you could participate in this session. Thank you. So the upper Midwest is a crucial region to the national methane budget, shown here as a bottom-up emission estimate. In the left, this is the U.S. livestock emissions from the graded EPA inventory. So the upper Midwest has very intensive agricultural activities. It includes 700 million livestock and the majority of U.S. hog facilities. In the red, showing as the wetland emissions. The upper Midwest is among the most wetland regions in the country. So in our region, most of the livestock emissions are in the south, while wetland emissions are in the north. This spatial pattern offers great benefit to separate emissions into sectors. To constrain those key sources, we performed the aircraft measurement in the Midwest across 3 seasons, shown here as the aircraft flight tracks colored by methane concentration. This aircraft is the one that we used for our winter flight. Air inlet is installed in the right wing. Most of the times, the aircraft will fly within 1 kilometer above the ground, so that the within mixing layer height methane concentration will be measured along with the flight track. The aircraft has 2 purposes. One is to constrain key point sources about livestock emissions that we have published in GGR. And the other purpose is to have a regional constraint on emissions, and we're going to present it here. Our study includes the combined constraints from GEM, ATOM, X-American, and Tall Tower measurement. So shown here is a summary of all those data sets. In the red, showing are the GEM flight tracks that we have seen in previous. In the left panel, across the Pacific Ocean, those are the ATOM flight tracks that we used to optimize model boundary conditions. We compare the ATOM observations with its simulations. And based on their 10% quantile difference, we develop a smooth spine function to latitude and apply it to boundary condition. On average, the correction is around 5 ppb. In terms of other model errors, we use the IGRA dataset to evaluate model planetary boundary layer. So in the red showing here, the 6 triangles are the IGRA sets. In the middle, it's the comparison of the PPL estimated based on IGRA and used in the model. The black lines are their average. So this data reveal less than 10% bias in the model PPL height. Finally, we use the X-American flight and the Tall Towers as independent evolution. And due to time limit, not show the details here, but the inversion result can successfully improve the simulation of those independent data sets for multiple years. Back to the inversion framework, we have 3 major inversions. The first one is a sector-based analytical inversion with fixed spatial distribution from prior estimate to directly solve for source attribution. The second one, we use Gaussian mixture model to spatially cluster grid cells, followed by an analytical inversion. This could directly solve for source attribution and a general emission distribution. In the third, we use GEOS-Chem adjoint to solve emission, to optimize emissions at 25 kilometers. Together, those inversions provide unique and comprehensive constraints to the Midwest methane flags. Here is our result. The results are consistent across those inversions. Shown here are the scaling factors aggregated to emission sector. Each row represents 1 inversion, with its sensitivity cases that optimize boundary condition as a state vector. The last row ensemble mean is the average of all those inversions. Each column represents 1 emission sector, including total emissions and livestock, wetland, and other emissions. We would like to point to 2 key messages here. First is the bottom-up underestimated of livestock fluxes. I'm going to detail explain later. The second one is the bottom-up overestimate of spring wetland fluxes. If we look into more details about the wetland emissions, we found spatial errors that are related with wetland type. Shown here are the optimized emissions of wetland and the optimized minus prior emissions from the GEOS-M inversion. Other inversions also provide similar results. We found in the northwest, the emissions are underestimated in the periportal region, where the hydrology is highly variable that influenced by groundwater flow and underground water flow, also influenced by snow and rainfall. Well, in the northeast, the emissions are overestimated in the coastal region, that the hydrology is mainly influenced by the Great Lake. Furthermore, we look into the uncertainty factors that are related with those errors. Shown here is a Taylor diagram of summer season. Other seasons also provide similar results. In this Taylor diagram, each point represents one case in the wet chart ensemble. In the wet chart ensemble, it includes 18 cases in total, each case using different assumptions to estimate wetland emissions. It includes 3 temperature dependencies as Q10 is equal to 1 or 2 or 3. Also include 3 scaling factors to scale the total wetland emissions. It also has 2 wetland extent data sets, either from GLWD or globe cover. In this Taylor diagram, the slope between each point to the original point is a spatial correlation between that case to the optimized flux, and the distance between each point to the observation point is a root mean square error. The color in this point is the emission magnitude relative to the optimized flux. First, we found wetland extent is a key uncertainty factor, that the GLWD estimate tend to overestimate emissions, but has a higher spatial correlation. Second, we found when Q10 is equal to 3, it has the lowest root mean square error. Back to the livestock emissions, we found manual management is a key uncertainty. Shown here is the optimized emissions and optimized minus prior emissions, also from GEOS-M inversion. We found livestock emissions are underestimated across 3 seasons, and the underestimated magnitude is summer higher than winter, higher than spring. Livestock emissions include 2 components. One is enteric fermentation, which is relatively flat across season. The second is manual management that has a temperature response. So that the different underestimated magnitude here point to possible errors in the manual management.
You have 30 seconds.
Yeah, so furthermore, because beef, dairy, hog has different spatial pattern in our region, so based on this spatial pattern, we further aggregated livestock scaling factor to animal types. For beef, more than 90% of emissions is from enteric, and the emissions are well constrained across seasons. But for dairy and hog, which has a higher fraction for manual management, emissions are underestimated by 30% in summer and winter, but well constrained in spring. We attribute it to lack represent of manual management in the inventory, such as applying manual to field in spring. Also, other manual management such as cover logging can also influence the emission estimate. And so in summary, we have high density aircraft measurement and performed a multi-inversion framework. We found significant spatial error and emission timing error in wetland and manual management emissions. So thank you. With that, I will be happy to take any questions.
That's great. Thank you very much for that really interesting talk. There's a question from Danielle. Could the underestimate in livestock emissions be due to increase in confined animal feeding operations?
It is possible, and we indeed considered, we did have some discussion on that, because our aircraft measurement was performed for 3 seasons, and the animal population is a little bit unlikely to significantly change across those 3 seasons in 2 years. But we found a significant difference in the emission correction in seasonality. So it is possible that the emission might attribute it to increase for animal population. But on the other hand, it's also highly possible that this is attributed to the manual management. Thank you.
And the follow-up question, I'm not sure it's a follow-up, but anyway, it was another question from Danielle. Does the TCON station in Park Falls, Wisconsin provide continuous information on methane sources in upper Midwest? Is the Park Falls site sensitive to the region that you're trying to estimate emissions for?
I'm sorry, I don't quite understand this question.
The TCON site in Park Falls, Wisconsin, is it sensitive to the region that you've been studying?
So, is this question asking for if this inversion result is only specific for the Midwest?
No, I think he was just asking you whether the TCON site in Park Falls, Wisconsin, whether that could help evaluate some of the estimates that you've inferred. Is it okay? All right, doesn't matter. We'll take that offline. We'll talk at the networking session. One quick question for you. I was quite struck by the spatial disaggregation. So even for things like dairy, beef, and hog farming, they are completely spatially different. And I'm trying to figure out whether they are. It's like that because I don't know why it's like that, but is your ability to be able to estimate sector emissions down to that level? Is it due to the fact that there is such a big different spatial distributions of these sectors?
We estimated the animal population based on the USDA estimate set to the county level and aggregated and combined the spatial pattern of the scaling factor and the animal population distribution to get the scaling factor for 3 animal types.
Okay, all right. Well, we can talk more at the networking session because I've got more questions. Okay, thank you very much. The last speaker of this session is Alice Drinkwater from Edinburgh. She's going to be talking about methane isotope ratios. Alice, you ready?
Yeah, I think so.
Okay.
Just gonna.
Ready?
Just.
Have you got permission yet?
Yeah, I think so. Oh, there we go.
Yeah.
Yeah. Okay, so I can. I've been having a few network issues, so we'll just see how this goes. Okay, so I'm going to be speaking about simulating methane isotope ratios using GEOS-Chem. In this presentation, I'm just going to be focusing on delta C13, but I've also been doing some work on delta D. So if people want to talk about that in the breakout session, that's absolutely fine. I'm happy to talk about that later. So I think all the other speakers this session have given a good introduction to methane, why we're interested in it. I'm looking specifically at methane isotope ratios. So I thought I'd give a bit of introduction into why we're interested in them, how they work. So normal methane is a carbon-12 surrounded by 4 hydrogen atoms, but you can get a replacement of the carbon-12 by carbon-13 or the hydrogen by deuterium. As I said, I'm just going to be focusing on those carbon replacements today, single substitution of the carbon. And when we consider these substitutions, we're looking at ratios. So we're considering the ratio of the carbon-13 to the carbon-12 in the sample. And these are represented as delta values. We've got the equation for it up there. So you look at the ratio, you compare it to a reference standard, and that produces a delta value. These are really interesting because they can be linked back to the original source of the methane sample. So if you look at this plot on the right, you can see if you're getting quite a light value of delta C13, it's more likely to be microbial. If you're looking heavier, it's more likely to be abiotic or thermogenic source. So these provide potential to be used as source signatures to be able to tell where your methane came from. And here I've just got a list of some typical delta C13 values for different source types, showing the sort of range that we might expect. Okay, so how does this work in practice when I'm using GEOS-Chem? So in order to create delta C13, what I've done is produce 2 different simulations, one carbon-12 methane, one carbon-13 methane. So I've got 2 completely separate simulations. And then in post, I'm combining them and producing delta values. My basis for this is the normal total CH4 run that many people will have used, but we have to make quite a few adjustments. The molecule weight and the decay rate with OH and the hard coding will need to be changed, and all the emission strengths. And we changed the emission strengths based upon those typical delta C13 values, which can then give you ratios, and it goes from there to produce a scaling factor for the emission strengths. So, as I say, my overall aim is to simulate delta C13. I'm looking globally using a 4x5 degree resolution. We'll talk a bit more about that later. And I want to do some inversions, and I'm looking from 2004 to 2017. It's quite a broad area. Okay, there we go. So first step when simulating carbon-13 methane is to do the spin up of GEOS-Chem. So what I've done to do this is I've simulated 2004 emissions and meteorology, and then just repeated 2004 again and again and again. So I'm repeatedly using 2004, and I do that, in this case, I think I did it for 60 times, and it's until the levels balance off and we're seeing properly balanced delta C13 values. So here's just an example at a bunch of different NOAA sites that I'll be using in my versions later, showing how you might think that it's balanced up one value, but then once you do this repeating 2004 or spin up, it actually balances off at a different value. Okay, so then I'm looking to produce a prior for my inversion. And to do that, I've done a set of inversions, but just 2004, not 2004 to 2017. And I'm using the real data from NOAA at a bunch of these different sites as shown here. And the idea is that we should get closer approximation to the NOAA sites, and that's what happens. So I was just solving for 2004, like I say, but then when I ran it over the full time period, hopefully get an improved prior. As you can see, from what I had was the blue line to what we ended up with in the orange line. It's a much better approximation to the NOAA data. It's still not perfect because you can see my attempt, the orange is sort of flat, whereas the NOAA looks like it might be getting a little bit lighter. And so that's where the greater inversion comes in. That's the steps that I took to produce a prior to do a forward simulation for delta C13. Okay, so then we come on to the inversion. As I mentioned, I'm looking from 2004 to 2017, and I'm using the maximum a posteriori solution. What I'm solving for here are regional signatures for delta C13. And the regions that I've split the world into are shown on this map here in different colours. So the idea is that if we see how the delta C13 signature from all the different regions are changing over time, we'll be able to get an idea of how the relative importance of different sources are changing within those regions. So for example, if we saw a shift that it was getting heavier in that region, that might suggest a shift towards more oil and gas energy emissions, and vice versa. If it seems like it's getting lighter, that might suggest that we're seeing more wetlands emissions, for example. And again, I've just shown typical delta C13 values there for all the different source types. Okay, so that's kind of the idea behind my inversion, looking at regional signatures globally. And here's an example of what the output might look like. So we have the prior, which is in orange, and then posterior is in blue. So these blue lines here should be improved estimates of the delta C13 signal from this region. And if we look at each site overall, each region, we see a few trends starting to appear. For example, if you look at boreal Eurasia, it looks as though we're getting lighter there, which might suggest more wetlands. Somewhere like temperate Eurasia, which is like around China, it seems like we see it getting heavier and then lighter possibly. A similar thing with tropical Asia, which might suggest a shift from energy and sort of coal and oil and gas burning towards wetlands, or a decrease in those energy sectors. But we can't read too much into this output until we actually check that we do see improved estimates. So what I've done here is I plotted what was my prior that we talked about earlier in blue, and then these regional delta C13 signatures that should be an improved estimate, got them in orange, but now we're looking at each NOAA site specifically. So we can make a much more direct comparison to the real data at these surface sites. And we're hoping that we should see improved estimation.
30 seconds, Alice.
Okay, no problem. So what I did was I made histograms just comparing at each site. And we do in fact see improved estimates at every NOAA site that I was looking at. So that suggests that we can place a little more weight in those conclusions that we were speaking about earlier. So here's some possible results and ideas and interpretations. That we seem to have a lightening trend from tropical regions, which might suggest a shift towards wetlands and biomass burning, and we see that in Eurasia as well. Okay, thank you.
Great, thank you. There's some questions here online. So how did the methane budget change when you just constrain the 13C? Would the result change if adding methane? It would change if adding in methane budget as an additional constraint. That's from Zen Chu.
Yeah, I think the final plan is to incorporate this with total methane and with the delta D. So eventually we would want to look at all three of them together. This is just focusing on the delta C13. But like I say, yeah, I think it would be ideal to include them all together.
Another question is from Chao Lu. Will it be good to jointly use? Oh yeah, that's the same question, sorry. Okay, that's the same question. There's a question from Matt Evans. My question is whether the chlorine has been looked at in this. Have you looked at chlorine?
No, so that would be something to consider. We have looked at OH and have looked at soil sink's been accounted for and OH has been accounted for, but chlorine I think I need to go back and look at in some more detail. That'd help. Thank you. Okay.
Thank you very much. That's the end of today's session. I want to thank all the speakers for giving really cool talks. I really enjoyed everything and some of the interaction there. I'm going to hand over to Eloise, who has some details about the schedule and timings for tomorrow. Eloise?
Sure, just give me a second. I just wanted to load the agenda before I said anything. Yeah, sorry, this is projecting a Word document, but it was just to give everyone a sort of idea of what was next. So there's networking with speakers, which will happen. We're running a little bit late, or actually we're not doing too badly. It'll start now for the next 20 minutes, and this is your opportunity to follow up on questions, ask some informal questions of the speakers, just to get to know a few more people. So it's filling in for the coffee line that you would have at an in-person conference. And then it's our second poster session. So I've just listed some of the titles here. You will have received an email this morning with the Zoom links for those poster sessions. And then also just to say, for the networking with speakers, you will have received Zoom links for those in the general attendee email that was sent out to everyone. Yeah, and I guess thanks to all the speakers today. There were some really fabulous talks, really interesting applications of GEOS-Chem as well.
That's great. Okay, see you in the poster sessions in the network room. Thanks. Bye.
Thanks, Paul.
Are we all good?
Yeah.